In this video, we'll look at the eigenvalues of a triangular matrix. So we're going to suppose that A is an n by n upper triangular matrix. This means that A has some entries along the diagonal that may or may not be zero. It can have anything above the diagonal, which I'll just indicate with a star there, but it must be zero below the diagonal. So everything below these lambda values along the diagonal are zero. Then, as you may have observed in the previous example, the eigenvalues of the matrix A must be the diagonal entries, the lambda 1, lambda 2 through lambda n. So if you have an upper triangular matrix, the eigenvalues will be its diagonal entries. Let's do a quick proof of that. Why is that the case? We need to look at the matrix A minus lambda I. If the corresponding homogeneous equation for this matrix has non-trivial solutions, then lambda was an eigenvalue. If lambda is not an eigenvalue, it's because it has no non-trivial solutions to the corresponding homogeneous equation. So let's look at this matrix. I have to take A, and I have to subtract this value of lambda along the diagonal only, and no other entries, including the upper or the lower entries, change. So I still have a upper triangular matrix. I now have these subtracted values along the diagonal. So this equation has non-trivial solutions if and only if, well, you have to make sure that you have at least one column that doesn't have a pivot in there, if and only if A minus lambda A has rank less than n. Remember, the rank is essentially the number of pivots in the matrix, and if there is a missing pivot in one of these columns, then you'll have a free variable in the solution set to this homogeneous equation, and therefore infinitely many solutions, non-trivial ones. Those will be eigenvectors. When are you going to have rank less than n? Well, you better make sure that at least one of these entries along the diagonal, these are the only places that pivots can occur, are going to be zero. So if lambda was lambda 1, for instance, the x1 would be a free variable. If lambda was equal to lambda 2, then there would not be a pivot in the second column, and you would have non-trivial solutions. Let's look at a quick example here. I'm going to take A to be this upper triangular matrix. Notice my diagonal entries are 2, 0, and minus 1. You're allowed to have zeros along the diagonal. All the non-zero entries are above the diagonal, and everything below the diagonal is 0. So this isn't indeed upper triangular. Therefore, the eigenvalues of A are my 2, 0, and negative 1 that I read along the diagonal. And in fact, because I have 3 distinct eigenvalues in a 3 by 3 matrix, I think that each eigenspace must be at most one-dimensional. In fact, if you look at the null space of A minus 2i, here's the eigenvalue 2, it's pretty easy to find a vector that if you multiply by A will just get doubled. If I take the vector E1, 1, 0, 0, and multiply by A, it will just select out the first column, and that will just get a factor of 2 as a result. It's pretty clear that the span of 1, 0, 0 is my lambda equal to 2 eigenspace. I'll let you, as an exercise, find the lambda equal to 0 eigenspace. That's the null space of your matrix, so the null space of A. And it turns out that it's the span of this one vector 1, minus 2, 0. At this point, you have two different eigenvectors for two different eigenvalues. This pair of vectors right here are linearly independent, and I have this third eigenvalue for lambda equal to minus 1. It can't be in the span of these two vectors. It has to be, in a sense, in another dimension of R3, in another part of R3. So I'll let you, as an exercise, just pause the video here. I'd like you to find the null space of A plus I, that is the lambda equal to minus 1 eigenspace, and you should be showing that it's the span of a particular vector that is linearly independent from the three vectors that we found here. Pause the video, and then when you resume it, I'll go through the calculation if you feel like you want to watch me do it. Okay, we're back. Here's my matrix A. I'm going to take 2, 0, minus 1. And if we're interested in the lambda equal to minus 1 eigenvalue, I need to look at the equation a minus lambda I. And because lambda is negative 1, it becomes a plus I. Ultimately, that means we're going to add along the diagonal entries my eigenvalue of minus 1. And so it's going to go up by 1 in this case, 3, 1, and 0. All the other entries stay the same. I then had the computer, in this case, row reduce for me, and I got 1, 0, 0, 1, 0, 1. You can notice there's a pivot in this column, only one free variable, and therefore there's only going to be one dimension for the eigenspace as we predicted. The solutions are x1 equal to 0, x2 equal to x minus x3, and x3 is a free variable, so in vector form the null space will be spanned by this vector 0, minus 1, and 1. So in conclusion, the null space of A plus I is the span of 0, minus 1, 1. Don't think that this is unique. Any non-zero multiple of this vector is also a vector that will span the eigenspace. So I just multiplied everything by minus 1 to illustrate this. Here is another eigenvector for lambda equal to minus 1, and it spans the eigenspace as well. Most importantly, in our discussion, we saw that it was one-dimensional.